Hello, everyone. Thank you guys for coming. We are waiting for James Chinn to join.
Everybody, I'm glad to see you all here. We're going to be starting in very soon.
Hello.
Hi.
How are you? Good to meet you.
Yeah, I'm Anushka. We've been emailing
you. Great. Yeah, great to meet you.
I'm Biosignature.
I like this background.
Cool. We had a short introduction for you. Do you mind?
Okay.
We do that.
Yeah.
Okay. Cool. Alessandra, take it away.
Okay, everybody, thank you so much for coming to the lecture with James Chinn on the physics of interplanetary travel. Before we begin, we have a little announcement to make about the physics club because we are hosting this lecture. We're actually also hosting a science fair as a fundraiser. So if you're interested in meeting a Nobel Prize winner at the award ceremony or winning a cash prize, please definitely sign up for that. This is the link, the URL. Last day to turn in entries is April 2nd, and it's free, open to all high schools. Okay, so here's a little introduction about our speaker. James Chinn grew up in Davis, California, and physics was his favorite subject in high school. He took 2 physics classes and he read a lot of pop physics books. He was especially interested in weird things happening at an atomic scale in high school. And outside of school, he played trumpet in a jazz band and worked as a tennis camp counselor in the summer. When he got to college, he focused mostly on the applications of physics rather than delving deeper into theoretic physics. And because of this, he decided to focus on engineering.
James Chinn also went to school at UCLA and studied mechanical engineering as well as with a side focus on electrical engineering. And during his senior year of high school, he took a nuclear engineering class and got along well with his professor, who just happened to be a nuclear radiation scientist at NASA's Jet Propulsion Lab. At the end of his senior year, he asked his professor asked him for a resume, and of course he gave him one. And then in the fall began working at NASA's Jet Propulsion Lab with the space radiation team. In the past couple of years, he's been moving around doing some radiation and electrical engineering and has been working on cool missions such as the Perseverance mission and the Europa Clipper mission. So without further ado, please welcome James Chinn.
Great intro. Those pictures were awesome. Yeah, great to be here. I understand some of you had my uncle, Ryan Chinn, as a teacher a few years ago. That's, I can't imagine having him as a teacher. I'm sure it was fun. So yeah, I've got some slides today that I put together to talk about what we're doing with the Mars Perseverance rover, some of the physics that we use to do the science there. And I've got some slides, like you said, on the Europa Clipper mission as well, and in particular, how we deal with the radiation at Jupiter. So I'll just get into it, unless you have anything else you want to do before. Okay, let's see. And I think I'll be able to see a hand raised or something, but if you have a question, just feel free to interrupt, talk over me, and I'll stop. Okay, so the first part of this is searching for biosignatures on Mars. Are the slides coming through okay?
Yep.
Okay, great. Go. So some of you may have seen 3 Thursdays ago, we landed on Mars. This is the rover descending to the surface. There's a video of this descent. If you haven't seen that, I recommend searching it on the NASA YouTube channel. It's very cool. And why did we land on Mars? Why do we want to know about Mars? Well, it's the closest thing to Earth that we know of aside from Earth. And we're interested in how life can arise elsewhere, whether or not it was ever on Mars, and how a place that we think used to be a lot like Earth with a temperate climate and water became the barren land that it is today. So we'd like to stay happy on Earth. We don't want to end up like Mars. So some of the more specific mission objectives we have are, like I said, geologic exploration to understand how Mars climate and geology changed over time. We're looking for signs of past life, whether or not Mars is habitable, and searching for biosignatures. And we'll collect samples on Mars, first time we've done that, and put them in a cache so that we can come back later, grab them, bring them back to Earth to look at in more detail. And then finally, we're preparing for human exploration. So we're measuring the weather on Mars and seeing how we can protect people when they land there and convert carbon dioxide to oxygen to use to breathe, but also for fuel so we can get people back home. So I'll focus on the habitability and biosignatures for the remainder of this. Right, so what is a biosignature? This here is the oldest biosignature found on Earth, about 3.5 billion years old. What we're looking for is a physical structure, like what you see on the left, in combination with a chemical profile, like you see on the right. Basically, we're looking for things that don't arise naturally. This type of combination of structures only happens when you have microorganisms creating gas in water. So these are the type of things that we're looking for in terms of biosignatures. And how we do that are with instruments like Pixel, which I've indicated here in that white box on the arm of the rover. It's also shown here on the descent picture. I don't know if you can see it. I'll give you a second. It is there. And on the ground, hopefully this one is easier to find. There it is. And finally, in the spacecraft assembly facility before launch, this is with the arm extended. You can see it right there. So the inside of Pixel looks like this. This is a slice horizontally across the ground. And what Pixel does is it, hopefully my laser isn't super laggy here, but it generates X-rays at this point and sends them to a target. And that target emits X-rays back, which Pixel observes and determines the chemical composition of. And then Pixel also takes close-up microscope type visible light images. So we get basically what I was showing before. We get the chemical composition on the right here and the physical structure on the left. So I'll get into how we build something like this, how we build an X-ray source that tells us the chemical composition of what we're looking at. And hopefully some of the physics that we do get into in a few slides here will be familiar to you. So here's a picture, a very crude picture of an atom with the nucleus in the center and two electron orbitals. When an X-ray comes in, sometimes it will knock an electron out of the atom. And when that happens, now we have an open electron orbital, or a more open, and the atom is unstable. Electrons in the higher energy will drop down and fill that orbital and emit an X-ray back out. And each element has a specific set of energies of X-rays that they will emit. So by shooting X-rays at a sample and measuring what comes back, we can tell what the elements are. So for instance, this is a spectrum from some sample. This is the counts of X-rays, and this is the energy here. So at 2 here, this is the peak where you'll see a lot of silicon. Calcium is about 4, etc. So we need to build a source of X-rays. All right, so what I just talked about is the part from the sample back to the source, back to the detector. What we need to do is we need to generate X-rays to hit the source, to hit the sample and measure them. Okay, so here's where we'll get into some of the physics that I think you are learning about, So when electrons slow down, they generate X-rays. It's called Bremsstrahlung, which is a German word that means breaking radiation. And what we need to do is we need to generate electrons and speed them up so that they can hit this target and slow down. We have a particular velocity that we're shooting for that will generate the right energy of X-rays. And we need to get electrons going that fast inside this tube here, this gray tube. Hopefully you can make it out. It's a certain distance, and we need to get the electrons going at a certain velocity. This equation here, I'm sure you have seen. The distance is 1/2 times the AT squared, acceleration times time squared. Sometimes there's a plus v0t here. Our initial velocity is 0. So this is how you relate acceleration in time to distance. And then you also know that velocity is acceleration times time. So we know the velocity we want, we know the distance we have, we can solve for acceleration and the time. The time is nice to have, it's not too important. Really, we want to know how much we need to accelerate these electrons so that we can generate our X-rays. So to accelerate things, I'm sure you know you need a force. You need a force on these electrons, and force is the mass times the acceleration. The mass, we know, it's the mass of an electron, and therefore we know what force we need. Okay, and then how do you exert a force on an electron? You do that with an electric field. So this equation may look familiar to you as well, I'm not sure. Force is the charge times the electric field. We know the charge on an electron, and now we know what electric field we need. So the last step is generating that electric field. Electric field is voltage divided by distance, which is the same distance here, the distance we have in our X-ray tube. So now we know what voltage we need to put across our tube. So yeah, with these equations that hopefully you're learning about right now, you can design an X-ray tube for the most part, at least the basics of it, to generate these electrons and look for biosignatures. So take a quick breather there to look back at this picture, which is very cool. And again, find Waldo. You may be saying, well, we still need to generate some electrons. So quickly going back, we need a source here for electrons. It turns out hot metals emit electrons. So the filament in your light bulbs, if they're incandescent light bulbs, are emitting electrons. They just don't have a big electric field that shoots them off and generates X-rays. That's why you're not constantly sustaining radiation damage in your house. We have a filament in this tube, and we need to get it to a certain temperature to emit a certain number of electrons so we can get a good reading from our sample. I think intuitively, we all know that to increase the temperature, you put energy in, energy into the sample. This next equation, I think you've probably seen. Energy is power times time. And this filament here is like a resistor. I think you've also heard talking about circuit equations. And so this will hopefully also look familiar. Power is IV, voltage squared over resistance. And so then we know what voltage we need to put across this resistor to generate the power, to heat up our filament, to generate our electrons and see our biosignatures. So just quickly going through that whole process again, we use these equations you're learning about right now to generate electrons, accelerate them to our target. Those emit X-rays to the sample we're interested in. That knocks out electrons from that sample, and higher energy electrons drop down to lower energy states. We can read back what those elements are and search for life. So that's the Mars part. I'll pause there if people have any questions, but I do have another set of slides on Europa.
We have some questions in the chat. Would you like us to read them to you?
Oh, great. Yeah, I couldn't, clearly I could not actually see what was going on. Yes, please.
You're on mute.
Sorry, okay. Sorry. One of the questions was, how was the crater that Perseverance landed in chosen?
Oh, basically we choose the site based on whether we think it has a high chance of at one point containing life. So we're looking for whether or not there was water there primarily. I can't speak to exactly why this crater was chosen over other craters, but in every case when we landed on Mars with Curiosity and Perseverance, we're basically selecting the site based on the chance of finding life.
Okay. Our second question is, which shell is the electron knocked out from? Or, yeah.
Yeah, could be anyone. And if you notice, if I go back, some of the, how do I go back? Here we go. You can sort of make it out. There's a cup. See, calcium here has 2 peaks, and so the energy that comes out of the atom depends on the difference in energy of the orbitals. And so if you have multiple orbitals, you can get different energies out of the atom.
Interesting. Okay, and our third question is, where do the electrons come from? Metal, will the metal lose electrons?
Ah, yes. Right. So what happens when you heat up the metal is temperature is a measure of how fast the particles are shaking. And if you get the electrons going fast enough, they can escape their attraction to the atoms. And yeah, they're sourced from just the sea of electrons on the metal, and we're providing a current from our power source.
Okay, we got 2 more questions. Could you ever confuse the energy signal?
Yes, as again, let me see if I find the bigger version of that. A lot of these peaks are very close together. I'm not going to be able to get there. I'll go with the small one. A lot of these peaks are very close together, and yeah, they can easily be confused. It depends on the, oh man, I'm all over the place, aren't I? It depends on the precision with which you can build the detector. Depends on how close the elements are that are contained in the sample. But yeah, as you can see, it's not super clean, so it is easy to confuse things.
And final question, has the helicopter on Mars made its first flight yet?
Yeah, I'm super excited about the helicopter. It has not flown yet. It should be in a few weeks. Right now, we're still checking out all the main functions of the rover, making sure the instruments work, making sure we can move around. But yeah, the helicopter will be coming soon, and yeah, very excited about that.
I have one more question. So you were saying it's how sensitive does the detector of the energy signals have to be in order to tell the difference between elements, and how would you keep that detector safe during launching and landing?
That's a great question. I didn't catch the very end of it. I heard how sensitive does it have to be. I can say that again, the peaks are very close together in a lot of these cases, so you do need pretty good resolution in energy. And you also need good resolution in the count rate here, because as the peaks also get close together, they start to merge together, and you need to be able to resolve the different peaks.
The other part of the question was, how would you keep it safe, like during launching and landing?
Oh, that is a good question too. Yeah, as you can imagine, a lot of this equipment is quite delicate. Let me back out of Expo here. Here it is. We have on the, let's see, can you see it here? Ah, yes, here. Let me, got all my stuff in the way. Anyway, you can see these arms here. They aim where we're looking at, but they also include a lot of shock absorption. So when you launch, the body of the rover is attached to the rocket, and so the vibration from the rocket goes into the body of the rover. The pixel is only attached by these legs, which have a lot of shock absorption. So the vibration on pixel itself is much lower, because you have that very sensitive filament, which is very, very small, and that could break. There's a lot of things that could break on a lot of these instruments, and we have to be very careful about loads like that.
Okay, we got 2 more questions in chat.
Okay.
But then after that, you can move on, and we can answer more questions later. Okay. How are the rover and helicopters powered?
The rover's powered by this here. It's called an MMRTG, multi-mission radio isotope thermoelectric generator. So there's plutonium in there, and it's generating heat as it decays. And there's materials that, when they have a temperature gradient across them, they generate a current. And so these fins coming off here are, on one side, they're touching the center, which is hot, and on the other side, they're cold. And so we end up with a temperature gradient across there, and that generates a current. It's not super efficient, but the plutonium will last a very long time. And we don't need to rely on sun, where dust can obscure the solar panels, etc. The helicopter does have solar panels on the top of it, and that's how it will charge. Right now, it's being charged by the rover, I believe, but after that, it will be on its own.
Is that the same thing that they were talking about in the Martian book that the main character goes out to go get?
The thermoelectric generator?
Mm-hmm.
It might be. I don't recall exactly, but it very well could be. It's used it on Voyager as well. It's used quite often.
Okay. And our last question was, like, does metal oxidize or reduce when the electrons come off of it?
It doesn't. I don't. That's a good question. It doesn't. The metal does not degrade very quickly when it's when it's emitting those electrons. But I'm not exactly sure the chemistry there. That's a very good question.
We do have some more questions. If you'd like to answer them, we can tell you, or would you have some time at the end to answer them?
I should have some time at the end. If they're related to Mars, we can do them now. But if it's kind of general, I'm happy to take them later.
These ones are related to Mars.
Okay.
Okay. What is the expected time for Perseverance to be working? Is it possible that it could run longer than Curiosity?
Yeah. Curiosity has been going for a very long time. And some of our other rovers as well have lasted a long time. We have our mission duration, which is what we design to definitely meet. But we're always over designing things to be certain that it gets to that point. And so almost always we end up going much longer than the design length. So it could be 10 years, hopefully, but we'll see.
And one more question, how is the temperature gradient formed?
Oh, on the thermoelectric generator. The plutonium is very hot and it's sitting at the center. These fins are being cooled by the convection from the air, and they're also radiating out. And so the outer surface of the fin furthest away is basically at Mars temperature, whatever that is at the time. And then the center where the plutonium is quite hot. And that's the gradient.
Cool. You may continue on to Europa now.
Okay, let's go to Europa. Very good questions. Everything looking okay?
Yep.
All right. So we're going to Europa. This is a very cool picture of the planets in the solar system and the sun. The planets and the sun are to scale. Earth, get the laser pointer back. Earth is above the laser pointer there. And Jupiter, I think you can see. So Jupiter's way bigger than Earth. And the sun is huge. I don't know if you've seen, there's YouTube videos that show this, and then even more so out to bigger and bigger stars. It's crazy how big some of those stars are. Anyway, we're going to Jupiter, and we're not this close to Jupiter in reality on this scale. If we were this close, Jupiter would be huge in the sky. Jupiter is quite far away. It is, you might think maybe it's over here or even twice as far away. It's actually on this scale 800 slide widths away from Earth. So if Earth was about the size of a pea and you put it in one end zone of a football field, Jupiter, about the size of a tennis ball, would be about 2 football fields away, very, very far away. And we're going to Jupiter's moon, Europa. Europa is about the same size as our moon. You can see our moon right next to us there. And so we're going to Europa, which is a moon around Jupiter, very far away. This is on the left there is a picture of Europa that's from Galileo. And if you were to land on Europa, it would look something like this middle picture here. So the whole surface of Europa is ice, and there are some plumes of water coming off the surface. It's close to Jupiter, so Jupiter is very big in the sky, and we're much further away from the sun. So the sun is only about a fifth the size as it looks from Earth, and it's dim. And below you, below the ice, is an ocean that covers the whole surface of the moon. And it's a very, very deep ocean. So in comparison to Earth, the deepest part of Earth's ocean is the Marianas Trench, which is 7 miles deep, we'll say it like that. We think Europa's oceans could be as much as 10 times that deep, 70 miles deep. And most of Earth's oceans are much shallower than the Marianas Trench. And so we're talking about a ton of water on Europa covering the whole surface. We think it is more water than Earth, in fact. And as I'm sure you know, that life likes water. Life as we know it at least likes water. So Europa is a promising place to search for life. The other thing Europa has going for it is sitting in Jupiter's radiation belt. So there's a ton of radiation hitting the surface of Europa, and that breaks apart the water, the H2O, into hydrogen and oxygen. And that oxygen can be used by organisms for metabolism to generate energy to build more copies of themselves. So we think Europa is a promising place to find life, and we're going there to get a better idea of what might be there. If it looks promising, we plan to land there. And if that looks promising, we're already talking about trying to get a submarine into the water. Okay, so the radiation at Jupiter is good for life that's below the thick layer of ice, but it's bad for our spacecraft, which does not have a thick layer of ice to protect it. So one thing you may have learned about is the V cross B effect, where a charged particle traveling from the sun or from interstellar space gets to Jupiter and sees Jupiter's magnetic field pointing down, let's say, and feels a force to the side perpendicular. So it starts to turn, and as it turns, the force on it also turns. And so these particles get trapped around the field lines at Jupiter. And Jupiter has a very strong magnetic field, so it traps a lot of high energy electrons, which can damage the spacecraft. So here's a little picture. On the left here is our spacecraft sitting in that radiation environment. And like X-rays can penetrate through materials quite easily, high energy electrons can do the same. So the electrons will go straight through the exterior of the spacecraft and they'll get into the electronics and they'll start to build up over time, and eventually they'll cause arcs. We'll have arcs in all of our systems on the spacecraft. To make an analogy, imagine you're in your car driving across the Bay Bridge, and you're pretty confident you're going to make it to the other side of the bridge. No problem, everything's working fine. Now imagine you're sitting on the bridge again, and you're sitting in a storm of electrons. There's electrons all around you. They're getting into your car. They're getting into the wires, and they're causing arcs. Well, maybe you're not going to make it across the bridge. Something might break. Maybe your automatic braking system will lock up. Maybe the timing on your engine will malfunction, and you'll get stuck. So we don't want that to happen to our spacecraft. In our case, it could be the thrusters. It could be our communication back to Earth. So we do our best to make sure that though we might have arcs, they aren't going to break anything, and we'll be okay. So now getting a little bit more technical again. Hopefully you're familiar with the equations here. Let's say we have a part on our spacecraft. Let's say it's the control for the thrusters. We know that these parts can take a certain amount of voltage, a certain amount of energy before they break. And we know we're going to have an arc coming in through the circuitry to our part. What we need to do to analyze the situation is model the discharge as circuit elements, as a capacitor and a resistor. And it turns out if you measure these arcs, this is in fact a pretty good way to model them. So a capacitor and a resistor. So what we need to do is, based on how the parts of our spacecraft charge up, we need to come up with a capacitance, a voltage on the capacitor, and a resistance to model them, and then we can tell whether or not our parts are in danger and whether or not we need to add protection to them. So here's two equations. These, hopefully you've seen them. One is the charge on a capacitor, Q, is the capacitance times the voltage. And another one is the energy on a capacitor, U, is 1/2 times CV squared, capacitance voltage squared. So in order for us to determine these values for our model, we need to know the energy stored in this part that's going to arc and the charge stored in that part. So here's an example of a part. This is this rainbow colored region here is a part on the radar for Europa Clipper. And we have software that has a different set of physics that transports the particles through the structure and tells us how much charge gets into various parts and tells us how much energy is stored up over time. So we have that from this other set of modeling tools that give us our stored charge and our stored energy. As you can see, again, we've got two equations, two unknowns, and we can get our capacitance and our voltage. So what's remaining is the resistor. This, you may have seen, the time constant of this RC circuit is resistance times the capacitance. And it takes about 3 time constants for the whole thing to discharge. So if we knew how long it took for our component to arc, we'd be able to tell what resistance is a good model for it. So again, going back to this part, we do in fact know something about how long it takes for these things to discharge. So when you do have an arc, what happens is you have a plasma cloud that expands out, and this covers the surface of the part and basically sucks up all the charge in the part and deposits it into the circuit wherever it goes. And people have measured how fast these plasmas can expand. So we know the, something happened with that picture. We know the velocity of the plasma. We know the distance it has to go because we know what our part looks like, and we can get the time. That's what it's supposed to, there we go. We get the time. And therefore we can back that out to the time constant and the resistance. And so we can do this for the various parts on our spacecraft and determine whether our circuits are good as they are, or whether we need to add protection in one location, add other components at another location, or perhaps add shielding or change the part so that it doesn't charge up as much, and we'll have happy circuits. Okay, that's all for that. Go back to questions if there's any.
So we have some questions in the chat. First one is why does the surface of Europa have red on it?
Oh yes, that's another important thing. So in addition to source of energy, let's actually go back to that. There we go. And so in addition to source of energy and what's that? And water, you need the right chemicals to form what we know as life. And Europa does have those type of chemicals. We think that this red is, some of that. And we have instruments on our Europa Clipper spacecraft to better identify exactly what they are. But an important part that I did forget to say is it does have, we believe, the carbon, hydrogen type of molecules that life as we know it needs.
Okay. Second question is, does Europa have salt or fresh water?
That's a good question. I don't think we exactly know. I think magnetic field measurements we've made of Europa indicate that there is some salt because we do seem to see electric currents flowing through the ocean. So I believe at this point we think it is salt water, but we will know a lot more about that once we get to Europa.
Somebody asked, would the radiation kill Europa?
Sorry, I missed that. Sorry.
Would the radiation kill life on Europa?
Oh, on the surface of Europa, almost definitely. yeah, we could, humans would die definitely on the surface of Europa. We don't think we'll find anything there. We're more interested in the ocean below it because it is protected by what we think to be probably miles thick of ice.
Next question is, are there water volcanoes? The spurts of water.
That's yeah, it's a good question. We definitely have seen maybe you call it a water volcano, maybe a geyser. But yeah, definitely high pressure vents that blow water into the atmosphere around Europa. And we plan to sample that when we go there. We'll have instruments that will fly as close to 25 kilometers over the surface of the moon, which is something like 15 miles. And the vapor from those plumes gets up that high, and we'll sample what's in there. And hopefully it'll look like there's, if not life, that would be awesome, at least the right ingredients for life.
The next question is, how do you ensure that the probe isn't destroyed by the asteroid belt? Do gravitational fields from larger asteroids affect the trajectory of the mission?
Good question.
And are we,
oh, there's one more.
There was just a little bit more.
Okay.
Are we able to communicate with the probe even when it's so far away?
Okay, yeah, so the meteoroids are a serious threat. We take that seriously. We have models of the asteroid belt and other particles that are moving through the solar system. And we have models of how when they impact the spacecraft, what kind of damage can happen. And that depends on the material of the particles, how fast they're going, and what material they're hitting on the spacecraft. So we do add shielding in sensitive areas. There's certain types of shielding, layered types of shields that are good at breaking up particles that hit the spacecraft and expanding them out and reducing the pressure on any one area. So we take that into account. As far as large asteroids that might totally blow up the spacecraft, we don't actively take into account most of those, because though the belt is dense compared to the rest of the solar system, there's not enough stuff that it's a high enough probability that we'll actually hit something. But will definitely get hit by lots of smaller things, and we design a spacecraft to be able to withstand those impacts. And then as far as communicating goes, yeah, we have a very big antenna, and yeah, we communicate via that antenna, call it our high gain antenna, high data rate. But there can be problems with that. Like for instance, on Galileo, our big antenna started out folded up. We thought it'd be a good safe spacing strategy to fold it up, but it got stuck trying to open. And so they had to go through all kinds of software changes and reduce data rates to use our, what we call a low gain antenna, which we didn't really intend to communicate with Earth in order to send data back.
Next question. Sorry, there's a lot of questions.
Yeah, no problem.
Why does Jupiter have a strong magnetic field?
That's a good question. Jupiter has conductive material in its center, like Earth does. And in terms of the strength, it must just be that it is either moving faster or at a higher, has more of it and or moving faster. It is about 20 times stronger than Earth's magnetic field. Once you account for how far away, you can't get as close to Jupiter as you can to Earth, because Jupiter is a lot bigger. So when you're approximately at the surface of Jupiter, it's about 20 times stronger than Earth's. But it's a good question. Exactly why it is so much stronger, I'm not certain.
Next, Anushka asked, why does water/ice block the radiation?
Yeah, that's a good question too. All matter slows down the radiation somewhat. Certain materials are better at slowing down certain types of radiation. If you have enough of anything, you'll block everything around Jupiter, say. At Europa, you have what we think of miles of ice, and that'll block definitely everything. On the spacecraft, we can only get, because we're limited by weight, we can only get millimeters thick type of material. And so that does not block everything, certainly. But yeah, any type of matter will slow down particles a little bit, at least, and eventually stop them.
The next question was, how would a potential submarine get through the ice? And would that release radiation into the water? That harmful forms.
I heard the first part about getting through the ice. I'll answer that, and then I'll ask you what the second part was. Yeah, it's a tough problem because it's thick ice and it's very cold ice. There's a couple different strategies. We've been talking to drill companies in Russia who often have to drill through ice. They use a drill. As you can imagine, getting a drill through miles of ice is difficult. Some other things that we've considered are to melt through the ice, so using a like an RTG with a radiation source and sinking through the ice that way. One of the tricky parts is you still need to be able to communicate with the surface so that you can get the data back. So you need to have a cable that you reel as you go down, or you need to leave relay stations that can communicate wirelessly through the whole ice. So it's a tricky problem, but really melting or drilling are probably the ways that we go. I didn't catch the second part of that question.
The second part was asking if melting or making some sort of hole in the ice would release radiation into the water and harming the life.
That's a good question. The water itself does block the radiation, and the majority of this radiation does not make the material radioactive. There's different kinds of radiation. Some radiation where you disrupt the nucleus of the atom makes the nucleus unstable, and that can release radiation on its own, makes it radioactive. The electrons aren't going to do that. They're just interacting with the electrons around the atom, and they'll ionize it, but they won't make it radioactive. So anything that does get to the surface of Europa is definitely going to suffer radiation damage, but by drilling a hole, we're not going to poison the water, you might say.
Somebody else asked a question. I don't think I'm sure what they meant, but whoever asked that question, do you want to?
Yeah. So basically, in addition to using drill, could we also use explosives as a way of digging down in Jupiter?
That's an interesting idea. Yeah, to get through miles of ice, you would probably need a lot of explosives. I'm sure if you used a nuclear explosive source, you might be able to get down there, though then you do run the risk of
contamination. Yeah.
Of contamination. But yeah, I mean, at this point, we really don't know how to get through it, and I'm sure explosives have been seriously considered.
Someone asked, are there ways to deflect radiation instead of absorbing it?
Yeah, that's also a very good question. We have been working on that as well, particularly for humans, because in order to get to Mars, the human in a typical spacecraft will sustain enough radiation damage that they're likely to get cancer. It's more than the allowed amount for an astronaut at this time. So we need to find a way to reduce that radiation dose inside the spacecraft in order to get people to Mars. One way is to just make the spacecraft heavier, add shielding to it, but that makes it harder and harder to launch. Another way is through active shielding, which I think is what the person who asked the question was getting at, is you could use something like an electric field to push radiation away, charged particles at least, or a magnetic field to do the same. So you could imagine having a magnetic field like Jupiter, say, around the spacecraft, where incoming particles would get stuck around the magnetic field lines, and they might go to they'd all kind of come to the poles, and you could have heavy shielding there, which blocks them, but you wouldn't need any shielding around the sides. That would be a lot lighter. You can use electric fields, electrostatic shielding, just having a strong enough electric field to repel particles. That one is challenging because there's both charge types of particles out there, so you need to figure out, you might be pulling something in, or you might be pushing it away, you don't know. And everything you pull in is a current that you need to sustain. So it costs more and more power to keep that going. If you remember, power is IV, P is IV, current times voltage, and you're trying to hold the voltage across these electrodes. If you're absorbing particles, you're absorbing a lot of current, and so the power that takes goes way up. So I'm of the opinion that the magnetic shielding is a better way to go, but both ways we haven't yet found a very good solution.
I don't see any more questions, but if I missed any, please ask your question.
Yeah, so my question is about the submarine on Mars. So if we have a submarine on Europa, would it have to be autonomous because of the thick layer of ice on top? But then I think you answered it with the cable going up, which could be a solution, I guess. But yeah.
Yeah, that's a good point. I think it would have to be at least mostly autonomous. In addition to being under the ice, Jupiter is so far away that it takes us roughly 7 minutes ish to communicate with a rover on Mars. Jupiter is up to 3 or 4 times further away than that, so it's going to take even longer to communicate with something near Jupiter. And combined with the issue of communicating through the ice, it's probably going to be mostly autonomous. Yeah.
Okay. If anyone has any other questions, do feel free to say them now, or
Yeah. So this is more for you, James, which is what did you do on your average day working at JPL? What were you doing?
So recently I've been doing a lot of tests for Europa, similar to what I was showing here. We have an electron accelerator that tries to mimic the radiation environment at Jupiter. So it's a very big machine. It's probably 50 feet long, and it's yay in diameter. And we accelerate electrons with 2 million volts, which might sound like a lot, but the electrons at Jupiter get up to 100 million volts or so. And we try to make the radiation environment as best we can so that we can measure discharges from things like this and do this kind of work that I was showing here. I do some simulation work as well. So the programs I was talking about that transport the particles through the spacecraft to come up with these stored energy, stored charge type things, do that too. And then obviously we have a lot of meetings and emails to organize everything.
A question.
Okay.
Who's allowed who's allowed to send something and get to the ice? Can anyone do it?
Yeah, I think anybody who could get there could do it. I don't think there's any laws about it, though. If you were, depending on how reckless you were, you might get spurned by the scientific community. But yeah, if you've got a way to do it, I say go for it.
So if I accidentally blew up Europa, I wouldn't get like put in jail or anything. I'd only just get.
Yeah, I think you just get mostly mean looks and probably some angry emails.
Okay, we have one last question. It is, what do you specifically work on for the robots you send to outer space? And what are the main factors you have to consider when working on a component?
Yeah, so as far as the Europa mission goes, like I was just talking about, we do a lot of testing for these kinds of parts. So we have, like, say the radar has certain components in it, and we need to know, are we going to be breaking things when these arc? So we'll model the components to figure out how they're going to charge up. We'll build up test articles, and then we'll test them in the lab, electron beam, and measure what comes off of them and make sure the electronics are okay. I'll also do, let's see, for the Mars mission, I was working on designing the X-ray tube. So the part that, here we go, that accelerates these electrons. We were having issues with it arcing, which we don't want it to do because it shorts it out and we can break it. So we have to design the shape of it pretty precisely to prevent arc. So we do, again, simulations, model the electric field in there to come up with a design that has low electric fields. And then again, we test it to make sure it works. So we'll turn it on and we'll put instruments in to measure whether or not it's arcing, see how it goes. So it's a lot of, we have a lot of simulation tools to model how we think things will work. And then we always test it to make sure that the simulations were correct.
And for the part that you were working on, like, I'm assuming you were working with a team of people. How big was that team?
Yeah, so for Pixel, it was probably about 30 people. The whole rover was maybe 500 or 600 people. So the teams get quite big, and organizing all of that is, fortunately, I don't have to do it, but it's quite the challenge, I'm sure.
Cool. You can go on, and if you have some time later, then we can answer some more questions.
Yeah, I've got, let's see, I've got to head out in about 5 minutes, but I'm happy to answer questions if there are any until then.
Okay. We have, oh, go ahead. Okay, we have one in the chat, which is, how are samples from Mars recovered?
Yeah, we are working on that mission right now. We're calling Mars Sample Burn. Basically, we need to bring a lot of fuel to Mars. We need to land on Mars. This Perseverance rover right now will collect a bunch of samples and cache them in a few locations. we'll need to land on Mars and either bring a lot of people with us, like I said, or use some of the technology on Rover right now, which converts carbon dioxide into oxygen. Often our fuel is just hydrogen and oxygen, makes water. It's a very exothermic reaction. So yeah, we'll land on Mars, collect the sample, launch back off of Mars, and probably just get into orbit around Mars. We probably won't bring enough fuel to get all the way back to Earth. Then we'll have a second spacecraft that go to Mars, collect that sample, bring it back to Earth. Into orbit around Earth, we'll either look at the samples on the space station or bring them back down to Earth and look at them here.
Cool. Isaac had a question about blowing up Europa. If we blow up, what will happen if we blow Europa up? Will its remains be sucked into Jupiter because of the gravity? Will it scatter everywhere? What will happen? What will it look like?
Yeah, good question. Yeah, I mean, it will blow up in its orbit, and a lot of it will probably go into Jupiter. Probably a lot of it will get into the orbits of the other moons and get sucked into them. Then you'll probably just have a big stream of debris, of Europa debris, near Europa's orbit and slowly spreading out. This is actually something we worry about a lot with blowing up satellites around Earth. They blow up and then the debris slowly starts spreading out across multiple orbits, and you end up having to design spacecraft that are more and more robust to damage. And if it gets bad enough, then it becomes untenable to send spacecraft up because they'll need too much shielding. And you may have heard of the Kessler syndrome, Kessler effect, where you start breaking things and then that makes it more likely for other things to break because there's more and more debris, and you end up with just a storm of metal up there where you can't send any more spacecraft.
Cool. We had another question. Is how do the iron bubbles in the calcium prove that life existed?
Are you talking about here? So basically, I think you're talking about here. Please ask again if this is wrong, but basically we don't see, I think the calcium we see all over the place, iron we see all over the place. What we don't see naturally forming is this physical structure, these cavities that look like this layered structure with this pattern of calcium and iron. We only see this when there's a layer of bacteria making it. So that's why if we saw something like this elsewhere, we would be fairly confident that it was also some type of organic process.
Okay. Next question. How was your workload while working on the Pixel?
The workload varies a lot. We'll have periods where it's pretty relaxed, where we're just working on the design, and then something will go wrong. And when something goes wrong, then the workload spikes up because we really got to make sure we fix it and get it done in time. Because as you know, we have specific launch windows where if we don't meet that window, we have to wait a long time for the planets to get back into alignment so we can launch again. So yeah, the workload fluctuates a lot. And if things are going well, this is the same everywhere. If things are going well, it can be a fairly relaxed time, but when things start going wrong, it can get pretty hectic.
How do you prevent life from Earth contaminating spacecraft?
Yes, we have a whole team, planetary protection team, that works on this. So everything is cleaned with chemicals, alcohols, etc. Everything is put together in a clean room with very, very low particle count. Some things we irradiate to get rid of microbes. We can't get rid of everything though. So that's a big problem. Is any spacecraft we send out is going to have something on it from Earth. And I'm sure if we do end up finding life anywhere, that's going to be the first question people ask is that there on its own, or did we put it there inadvertently? But we do try very hard to keep the spacecraft clean so we don't get, bring life elsewhere.
Okay, cool. One last question, and then I know you have to go somewhere. Isaac, I was wondering what happens to Europa when you blow it up. What happens to all the water on it?
The water, while it's on Europa, it's insulated from the cold by the ice, and it's being squashed by the tidal forces of Jupiter and the other moons. So the water stays kind of warm. If you blew up Europa, that water would not have that same force. It would be in much smaller quantities, probably all freeze and form ice. Yeah, it would just start raining down on Jupiter and the other moons, and it would. I don't recommend it. Even if you could do it, like I said, go for it. But now I think I'm reconsidering it. Please don't blow up Europa.
Cool.
Thank you so much.
You.
Okay. Yeah, no problem. Happy to do it.